Hello everyone, welcome back to part 5 of Neural Networks Explained, and I'm Pooky Code, and we're going to look at different activation functions such as Sigmoid and ReLU. Let's get started. Alright, so we remember that step of x is defined such that it is 0 if x is smaller than 0, and 1 if x is bigger or equal than 0. And this gives us a function that looks like this. So a flat line at 0, and then when x becomes bigger than 0, it becomes a flat line at 1. And so now I'm going to introduce you to Sigmoid. And Sigmoid, it's called Sigmoid, and it's denoted with a symbol like that, so kind of like an O with a bar. And Sigmoid of x is defined as a function of 1 over 1 plus e to the minus x. And what this means is that it basically is a smoothed out version of the step function. So this looks like this if you plot it. And what's important to know is not to remember what the formula of sigmoid is, but it is important to know that it is basically step of x, but it is smoothed out, so it's continuous now. And then, the one that I'm going to talk about is ReLU. And ReLU of x is defined as 0 if x is smaller than 0, and x if x bigger or equal than 0. So this gives us a function that looks like this. So 0, 0, 0, 0. And then when x becomes bigger than 0, it rises at the same time as x increases. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. And what are the advantages of ReLU? ReLU is a function that is much easier to compute than sigmoid, and it yields better results than sigmoid and step. So some of you may be confused and say like, what the hell happened to our step function? I thought that like sigmoid, I guess it makes sense because it's just like step of x but smoothed out. But why would ReLU work at all? It's literally like not the same function at all. So if you recall from the previous videos, we know that the goal of having multiple layers in a neural network was that so each layer could simplify the input so that it will pass it to the next layer. So basically, it's not why ReLU works in particular, but it's more because we need a nonlinear activation function, and ReLU is nonlinear. So why do we need an activation function that is not linear? It's because if it was linear, that will mean that all of the layers can be combined into one simple linear layer, and you could have a neural network of 1000 linear layers and you still won't be able to solve the XOR problem, which is kind of stupid when you have a neural network with 2 layers with the step function that can solve the XOR problem. So, how does it work? It's basically that when you have linearly separable problems, you know that they can be expressed by linear expressions. So for example, let's say I have this neural network that is composed of multiple linear layers. I see that at layer 1, I just have x1 and x2. At layer 2, I have x1 plus 3x2 minus 2. And then I have 2x1 plus 4x2 minus 3. This is basically just taking the weight, multiplying it by its input, and for both of these inputs, and then you add the bias. And then for layer 3, we take the inputs from layer 2 and we apply the weight. So times 3, then times 5, and then minus 6. So this gives us 3 times x1 plus 3x2 minus 2, and so on and so on. And then this gives us, in the end, when you develop and you simplify it, it gives us 13x1 plus 29x2 minus 27. So here we see that our 2 layers could have just been expressed as a neural network with just like this. So x1, x2, a weight of 13, a weight of 29, and then minus 27. Instead of using this neural network with so many layers, like 3 layers, we can now reduce it to 2 layers. And this works for any number of layers. So if you have 1000 layers, linear layers from a neural network, it could still be able to be expressed as one neural network that only has an input and an output layer. So basically, ReLU works because it is nonlinear. And by the very property that it's nonlinear, it works for us because this allows us to not be able to mash all the layers into one linear function, because when you add the nonlinear function, it becomes like it becomes impossible to squish it into just one linear expression. So for the next topic, we're going to look at matrix notation, so how we can express weights and biases in a more compact form instead of using B1, B2, and so on. And we're also going to learn about gradient descent, backpropagation, and how neural networks learn. So see you next time. So thanks for watching. If you like this content, like, subscribe, hit that bell icon, do whatever you like. And next time we're going to look at matrix notation. So stay tuned.